This is going on page 104. Okay, so yesterday we had a lot of vocabulary regarding circles. We have some more vocabulary today, but also some rules on how to find some different measurements. So first vocabulary word is a central angle. Okay. Central angle is an angle whose vertex is at the center of the circle. So there are lots of angles that relate to circles, and we're going to look at the different angles and how to find their measures and whatnot. But the central angle is the easiest, and it's the one we're going to use the most, kind of the most important to apply to a lot of things that we need to do. So we need to make sure we fully understand this before we add more angles later on down the road. But if the vertex is at the center, that makes it a central angle, so that this right here is an example of a central angle. Now, if you have a point inside of a circle that looks like it's at the center, it's the center of the circle. Nobody's trying to trick you. It's not that you're assuming anything. Even here, this angle here, we've got this B, which there isn't like an actual dot there for the point, but still B is the center. You're not, again, not assuming anything. Nobody's trying to make it just a little off or anything like that. So, along with those circles, along with circles, but in the central angle, we have an arc. The word arc isn't a brand new word for you for sure. I'm not so sure if you really have talked about those with circles, but an arc is an unbroken part of a circle consisting of 2 points called the endpoints and all the points on the circle between them. Basically, an analogy is an arc is to a circle like a line segment is to a line, just a part of it. So here's my circle from R to S. This right here would just be an arc. I think that should hopefully make sense. We name the arcs by their midpoints, so this would, not by their midpoints, by their endpoints. So this would be arc RS, capital letters, you put the arc over it. So the arcs and the central angles are related. So with this central angle right here, we have this arc right here, which is called the intercepted arc. Not the intersected, like intersecting lines, but intercepted, like I intercepted the football. So like if I put my arms out and I intercept the football, it's just like putting the arms of the angle out and intercepting that arc. If I close the angle, that's the intercepted arc. Does that make sense? So that angle and that arc are definitely related to each other. We're going to see how right here. All right, so our different kinds of arcs. First one is a minor arc. Okay, so a minor arc is an arc whose points are on or in the interior of the central angle. So just like we have an interior and exterior of a circle, we have an interior and exterior of an angle. So this is the interior of the angle, and then this would be everything else outside of it would be the exterior of the angle. So if you close the angle, you squish the interior, right? So this right here would be my minor arc, because if angle B is my central angle, then that right there is the arc that's on the interior of the angle. So the measure of a minor arc is equal to the measure of its central angle. Like I said, it's a very easy relationship, but there's different ways to talk about arcs. We can talk about their measure and their length. Today we are just looking at measure, and you measure an arc in degrees just like you would an angle. Arc length is something different. So if we think of this as a circular track and we're running around the track, right? So if I run from A to C, I could run maybe 50 yards, or I could run 80 degrees. But those are two completely different types of measurements. And if I'm going to run from A all the way around the circle back to A, that's 360 degrees, no matter how big my track is. But how big or small the track is changes the actual distance I would run. Does that make sense? So do you see how you're calculating two different things? We will get to arc length later on, maybe next week, but right now we're just talking measure, so it's all in degrees. So if this angle right here is x degrees, then the arc measure is also x degrees. So the measure of angle B is equal to x degrees. And then that is arc AC. So we put the little m in front of it to represent the measure of the arc. And that's also equal to x degrees. And that is a minor arc. Next one is a major arc. It's an arc whose points are on or in the exterior of the central angle. So angle B is my central angle. This was the interior, so this is the exterior, and it's part of the circle, so it's this right here. So if I know the measure of the central angle, how do you think I can find the measure of a major arc? Subtract it from 360. Good. So the measure of a major arc is equal to 360 minus the measure of its central angle. Okay. So we know that the measure of angle B is x degrees. Now the endpoints of this arc are AC also, just like it was on the one right above it. But the difference is, it's a different way to get to C. Because again, if we were running around a circle, I could start at A and end at C, or I could start at A and come around here and end at C. Two different ways to get there. So I got to be able to distinguish between the two, which means I can't just call this arc AC. So I have to name it with 3 letters. A and C are still the endpoints, but I got to go through D to get there. So this would be called arc ADC. Okay? Because again, start at A, end at C, but you got to go through D to get there. That's going to be equal to 360 minus x degrees. Any questions? All right. Then if the endpoints of an arc lie on a diameter, which if you look at this picture over here, EG looks like the diameter, but you don't actually know for sure based on this picture. You know for sure EG is a chord, but that's the best you can do. If I do this, now we know it's the diameter. Does that make sense? So EG is the diameter, so the endpoints lie on the diameter. So we'll say that this is our arc. What do you think that's called? Because you know this word, you've known it for a while. Just may not realize it. How much of the circle is it? It's a semicircle. Good. So this is a semicircle. Okay. So the measure of a semicircle is what? What? 180. That's half of 360. Good. 180. Now, even though it's 180 whether I talk about the top or the bottom, I still got to know which piece I'm talking about, so I still have to use 3 letters. So the measure of arc EFG is equal to 180 degrees. Okay, everybody good? Minor arc, major arc, semicircle. Then a little bit about notation here. Minor arcs may, which means you have options, may be named by 2 or 3 points. Most of the time, minor arcs are named by 2, but you can name a minor arc with 3 points if you so desire. Not really necessary, but you can do it. Then major arcs and semicircles must, which means you don't have an option, must be named by 3 points. Thank you. All right, so if I have an arc and it's named by 2 points, that guarantees me it is a minor arc. If it's named by 3 points, I would have to look at a picture or have a number to know. And that's no guarantees because it could be any of the 3. Okay, everybody good with that? All right, so then let's look at this example here. We got a circle graph or a pie chart, and look at it a couple of different ways. I know you've seen these before and done these. So each one of these little sections has percentages in them. All those little percentages should have to add up to give me what? 100. Okay. So they're going to have to add up to give me 100. I know that much, right? And I'm looking first for the measure of arc BC. So let's find that. Here's arc BC. And I know that the measure of that arc is the same as the measure of this central angle. So if I could figure one of them out, I know the other one. So that's 13%. That 13% is 13% out of what? 100. So it's 13 out of 100. Right? That is related to that angle, which is a part of how much? 360. So that goes with x over 360. Right? It's a proportional relationship. Anytime you can make something into a proportional relationship, go for it, because y'all are good at that. Makes sense. Now, We've been talking a lot about how to work smarter and not harder, and you don't have a calculator in front of you. So let's think about what we're actually going to do. We need to multiply 13 times 360 and divide by 100. So let's just write down what that means. That means I would do 13 times 360 divided by 100. That's what would actually happen, right? But I would really rather not do all that crazy computation because those are big numbers. What I know from basic math that we know is that I can knock off those zeros, right? It's basically like dividing them both by 10. So I've simplified it a little bit. So if I simplify it any more like that, I'm going to end up with decimals at this point. I don't know that I really want to do that. So we're going to leave 10 in the denominator. And in the numerator, I'm going to multiply 13 times 36. Now, 13 times 36, that's the same as 10 times 36 plus 3 times 36, right? So it's 10 times 36. 360. So I'm just going to write this down so I don't lose track of my numbers. So I did 10 times 360. 3 times 30, 10 times 36, I'm sorry. Then 3 times 36, so 3 times 30 is what? 90. 3 times 6 is 18. 90 and 18 gives me 108. So 3 times 36 is 108. So there's my 10, there's my 3, so I add them up, which tells me 13 times 36 is 468. That makes sense? Now I've still got this, and it's not going to divide evenly. We are going to be able to get decimals here, though, because we're talking percentages. So 468 divided by 10 is super easy. What does that give me? 46.8. You just move the decimal place. So the measure of arc BC is equal to 46.8 degrees. Everybody okay with that? Now, you know, some of y'all would have been doing some crazy math out to the side, right? And again, I'm not saying that you have to always do everything in your head. Jotting a few things down, doing a little bit of stuff, that's fine. But there's absolutely no reason that I would have actually needed to multiply 13 times 360 if I can understand how the numbers relate. We good? Okay. All right, so then let's look at the measure of angle FMC. Okay, so FMC is this angle right here, which would be the same as this arc right here. And that's more than one piece of that pie. So I would need to add some of those things together. What would I be adding together here? 9, 10, and 11. Do I add that 3? No. Everybody always wants to add the 3 because it's right here. But, ooh, goodness. I could just get through one class period without that happening. Starts at F. This 3 actually goes with this right here, and that's not what we're looking for. So it drops down there, but we're not using it. So we're adding 9, 10, and 11. So 9 plus 10 plus 11 gives me what? 30. So that's 30% is what we're looking at. So that 30% is out of 100, and I'm looking for the angle, which is out of 360. Okay. Now, I wouldn't suggest a whole lot of reducing at this point necessarily, meaning if I had to really think hard to reduce a fraction, I don't know that it's worth the time right now because you can kind of do it at this next step. But when it's something simple like that, go ahead and make that 30 over 100 down to 3 over 10. It's a quick way to just kind of narrow things down a little bit. Then when I cross multiply, that's going to give me 3 times 360 divided by 10. Right? Then again, I can knock out those zeros. So it really just leaves me with 1 in the denominator. And so I'm really just doing 3 times 36, which we actually already figured out is what? Remember we did 3. Yeah, it's 108 because we already did that. Measure of angle FMC is equal to 108 degrees. If you can understand how numbers relate to each other and what's legal and not legal when you're manipulating them, you can simplify your life a lot. Just make sure you understand when you're doing stuff like that, you're not dividing it by every single number. That's only if there's more than one term. Okay, but when it's all multiplication and division, it can divide out this way. Questions? Also look at reasonableness of an answer. Because you've got like 100 or 360 is a little bit more, it's little more than 3 times 100, right? So if I look at 13, I can round that to 15. So 3 times 15 is 45. So this number should be in the ballpark of 45, and that's what I've got. And again, this is a little bit more than 3 times 100, so this should be a little bit more than 3 times 30, so it should be a little bit more than 90, and I get 108, I feel like they're reasonable answers, right? So you can always use estimation just to make sure you're in the right ballpark there. Okay, moving on. Now we are going to talk about adjacent arcs. We've talked about adjacent angles. Remember that they're connected to each other. There's no overlaps or anything. So same kind of thing here. There are two arcs in the same circle that intersect at exactly one point. So there's no overlaps or anything. In this picture over here, that would be arc RS and ST. Kind of think of them like snapping together. So RS and ST would be your adjacent arcs over here. Then we have the arc addition postulate. We've had an angle addition postulate and a segment addition postulate. Arc addition postulate says pretty much the same thing too. Piece plus piece equals the whole thing. It's the rule that allows us to actually add the pieces. So the measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So that means in this case I would have the measure of arc RS plus the measure of arc ST, and that's equal to the measure of arc RT. Okay. Questions about that? All right. Moving on then. So now we are going to actually find missing pieces. And we're not going to have to write theorems and stuff to justify things. We need to think about them, of course, but sometimes using different colors on these really helps people. If you're not into the whole different color thing, or you just don't have them, making things darker or squiggly or whatever to separate them can be helpful. But always mark things on here, label numbers that you find. If you get stuck on these, instead of being focused on, I can't find what it's asking me to find, forget what it's asking you to find, go find everything else you can find, and then go back and look at the question, and I bet you have enough information now. You just kind of get that tunnel vision sometimes. And at the very, very least, mark what you're looking for. So in this first one, excuse me, we're looking for the measure of arc CDE. That means I start at C, I end at E, I go through D to get there. So that is the arc that I'm looking for. Okay. Then we know that the central angle in the arc has the same measure. So what is the measure of just arc CD? 90, because if that's 90, this is 90, right? So if I can find the measure of arc DE, then I can add them together, and I'm good. Can I figure the measure of arc DE out? What do you think it is? 18. Because this angle is 18, so this angle is 18, because they're what type of angle pair? Vertical angles. And then since this angle is 18, that means this arc is 18 degrees. So I have the two pieces, and I can just add them together, and the measure of arc CDE then would be what? 108. The popular number of the day. There's no such thing as vertical arcs, by the way. Sounds like there should be, like it would make sense, but we got vertical angles that helps us with arcs. All right, so I'm going to give you a couple minutes. I want you to find the measure of arc JKL, and if you get that one, then move on to LJN. I may not give you enough time to do both of them, but label, mark stuff on your picture. Okay. So I'm going to get somebody to help me, and if you're not finished yet, that's okay. I want to know where you've gotten to. Okay. Ruben, have you found the measure of arc JKL yet? Okay. Now, I'm going to pause for just 1 second. Let me mark what I got ahead of myself. So we know we're starting at J, we're ending at L, we're going through K, so we're looking for this. Okay. Now, tell me what you just said. Okay. KJ is 25. Good. So we know that this is 25, right? All right, and then you were stuck? Okay. So let's see. We can walk, there's lots of options here, so we're going to go through it one way, and then we're going to talk about the other ways to see it, and then see if anybody else had anything else. Somebody last period had something I wouldn't have done. But so if I can find KL, then we'd be good, right? Do you see a semicircle here with KLN? You see that? So if I know the total of this, like what's 40 and 25? 65. So this whole thing here is 65, right? Can you use that to help you find KL, Ruben? Because what does a semicircle measure? 180. So if I do 180 minus 65, then I can find it. So what's 180 minus 65? So do 180 minus 60 gives you 120, and 5 more gives you 115. Okay, make sense? All right, so then because what we want is JKL, when I add those together, what's the measure of arc JKL? It's 115, 140. Good. Does that make sense? Okay, good. Any questions about that process? Because there's different ways. All right, somebody want to tell me a different way they did it? Or is that how everybody pretty much did it? Okay, let me talk to you about a couple of different things. So last period, somebody tried to walk me through it, and I was with them, and then I realized at the end what they were saying really didn't make sense. But then somebody else had done kind of what they did on the same line. So this is what somebody told me last period. She said, well, we had these vertical angles. So she said, so then I drew in the other 40-degree angle, right? So that she could add these two, which is 65, and these two, which is 65. Then you notice that what's left right here would have to be congruent to KL. Does that make sense? So she added all 4 of these up, subtract from 360, divided by 2, and that's how she got 115. Totally works, right? And then kind of did the same adding there. Or do you see how, we used KLN as the semicircle. Do you see this semicircle right here? So if this is going to be 180, couldn't I just take 180 minus 40? Does that make sense? And then get 140 that way? Any of them work. Is one better than another? Not necessarily. It's whatever makes sense to you and whatever you can see. Okay? We good so far? All right. Let's talk about LJN. See, even if you haven't actually found it yet, if you could help talk me through it. Laisha, did you have a chance to actually find LJN yet? Okay, so let's mark it and let's do this together. So this means we're gonna start at L, we're gonna end at N. We're gonna end at N, but we go through J to get there. Looks like that. Okay. So that's what this means. You start at L, you end at N, you go through J to get there. Got to go the long way. Okay, so Laisha, can you just tell me what you're thinking or what might be helpful here? How maybe we could do this? Measure of JN. Okay, so the measure of JN, this right here is, this part is 155. Okay, so then what will we do with that? Good. So we can add the 155, the 25, and the 115 all together. And what do you get when you do that? Turn that off, please. Close. 295, because remember these together is 140, so if I take 140 in that, I get 295. Okay, good. All right, so did y'all follow her logic there? You good with that? All right, anybody have a different way of doing that? That would work? Does that make sense to y'all? Will that work too? Did you have something different, or is that what you did? Okay, awesome. Yeah, either way, because look, if we didn't do it this way, the green way that we talked Ruben through, let's say I just did the 180 minus 40, I wouldn't have had anything actually labeled on there yet. So in order to do it one way, I'd have to actually go find those things so that I can add them up. Or I could just get that 65 and subtract it from 360. So most of the time on these, you kind of need all the pieces anyway. So I like to approach them as not even really looking at the problem, go and label everything I can possibly label, then go read the question, and then it makes it just fly a lot quicker, and you're not stuck trying to find stuff you just don't know how to find. Because in most of these, you have to find something they didn't ask you for to find something they did ask you for. Okay? Questions? Just know there's most all the time more than one way to approach it. Okay. All right. So next thing is congruent arcs. Congruent arcs are two arcs that are in the same or congruent circles, so they could be in two different circles, and have the same measure. So that should make sense, right? So if we know that these two angles have the same measure, that means the arcs have the same measure, which means they're congruent. And you mark them congruent like you would line segments with the little hash marks. And then we have these three theorems that all kind of go together. So this first one says, in a circle or congruent circles, congruent central angles, so they tell us that these two angles here are congruent, have congruent chords. Because we've talked about the arcs and the angles, but there's also, if you connect the two endpoints of the arc, it creates a line segment, which is also a chord. So if I know my angles are congruent, then my conclusion can be that the chords are congruent. So DE is congruent to BC. That could be my conclusion. If they tell me I have congruent chords, like they do in this one, then that tells me I have congruent arcs. So that would give me here then that arc DE is congruent to arc CB. So. And notice whether I put a line segment above it or an arc above it, it doesn't matter what the order of the letters are, but I'm talking about two different things, right? This is talking about the chord, this is talking about the arc, so notation is important. Then, if I have congruent arcs, that means I have congruent central angles. So here they tell me the arcs are congruent, which tells me angle EAD is congruent to angle CAB. I kind of feel like this could all just be written as one big thing because, like I said, they all go together. This tells me that if I have congruent arcs, then my central angles are congruent. And then if my central angles are congruent, then my chords are congruent. Right? So basically, if one of these three pieces that relate to each other, if you have one set of congruent things, it automatically makes the other two congruent. It just takes a couple theorems to get there, but it's all the same. Questions? All right, awesome. Next page then. It says applying congruent angles, arcs and chords. All right, so it tells me that RS is congruent to TU. That's what I know. Since the chords are congruent, I know that the arcs are congruent. So I can set them equal to each other. 3x equals 2x plus 27. So that's going to give me x equals 27. Super easy, right? Don't want x, I want rs. So I do 3 times 27. 3 times 20 is 60. 3 times 7 is 21. 60 and 21 is 81. So the measure of rs is 81 degrees. Questions? The work should all be super simple on these. It's just applying the idea of what parts are congruent, of course. Okay, so here, this tells me my circles are congruent, and it tells me that the arcs are congruent. That means these central angles have to be congruent. Then the angle that we're looking for sort of disappeared back here. This is DEF is what I'm looking for. So since they're congruent, I set them equal to each other. So 5y plus 5 equals 7y minus 43. So 48 is equal to 2y, and y is equal to 24. Okay. And I don't want y, I want the measure of the angles, so I've got to do 7 times 24 minus 43. So we're going to make 24 25. You got 7 quarters. How much money do you have? 175. But I didn't want 25 of them, so once I get my 175, I got to take 7 away. So it gives me 168 minus 43. So the measure of angle DEF is equal to 125. Questions? All good? Okay. Next theorem. In a circle, if a radius or diameter, okay, because here we have, this is the radius, obviously, but if this was the entire diameter, the same thing would be true either way. And because we have a radius and a chord. So what this tells me is that if a radius or diameter is perpendicular to a chord, which it is right here, then it bisects the chord and its arc. So these are congruent, and these are congruent. So not every chord bisects each other or anything, but if it's a radius or a diameter and it's perpendicular, then it bisects it. So we're going to add a letter in here. We're going to add a G so that we can talk about that and say that line segment EG is congruent to line segment GF. We also know that arc ED, oh, that would not be an arc, would it? Arc ED is congruent to arc DF. The next one is basically the converse, but not directly. And in addition to that, we need to pretend like that point isn't there. I meant to take that off. Because what it's saying from the beginning here is that you just know that JK is a chord. That's it. You don't necessarily know that it goes to the center. All you know is that you have a line that is this line segment is the perpendicular bisector of this chord. So if this is the perpendicular bisector of this chord, then it is a radius or a diameter. So your conclusion is that line segment JK is a diameter. Questions about that? All right. So let's look at how we're going to handle this. In this circle here, we want to find the length of BD. So somebody tell me something about BD. It's a chord. Yes. So we know it's a chord. It's bisected, right? Because this is perpendicular. So since it's bisected, I'm going to mark that there. Notice that this other piece didn't necessarily get bisected. It's possible, but not always happening. So I need some way to solve for that piece that I don't know. So I could draw in to make a triangle, and I can draw the radius in anywhere. So I'm going to draw it in somewhere. I mean, I could draw it over here. That's not going to help me any. Oh, goodness. It's not going to help me over there either. But if I connect this, bam, then I made myself a little right triangle. So what I'm going to do now is I don't really want to call BDX, even though that's what I'm looking for, because I'm only going to be able to use part of it. So I'm going to call this part X and this part X and just know when I'm finished, the answer I get for X is not my final answer. That's way better than calling the whole thing X and using 1/2 of X to do anything. All right, so I've got a little right triangle. I would need to label that hypotenuse as something. What do you think I could label that as? 5, X, Y, 3? What do you think? What part of the circle is line segment AB? The radius. So what can I label it as? 5. Somebody said 5 and then they didn't say it again. I think they second-guessed themselves. Isn't EA also a radius? Now to me, in these pictures, and this circle is circular. It's like truly a circle. Those line segments are truly line segments. Even the purple one I drew is pretty close to being straight. But to me, those two radii don't look congruent. Like it's like an optical illusion or something when you draw that chord through there. So I think that's sometimes what throws you off. But if this whole thing is 5, then this whole thing is 5. It has to be, right? Because it's the radius. So what would I do to solve for X? Pythagorean theorem. So X squared plus 3 squared equals 5 squared. What does X have to be? It really wouldn't take any work. 4. This is a 3, 4, 5 triangle. If you don't recognize it as that, it's totally fine because you can do Pythagorean theorem and it's super easy. I'm just not going to write down all the steps. Okay. It's okay that you don't know the triples. It really is. But again, some of them just become recognizable. So X is 4. So I got to multiply it by 2 to get that the length of BD then is 8. Everybody okay with that? All right, good. Okay, so you work on the next one while I pass out the homework. Okay, so that's what I got. Do you agree with me? Yes, okay. Would I have really had to do all of that work? Not that it's hard. I mean, that's something you're capable of. It's a lot of stuff to write, but it doesn't work out that horrible, so it's something we could do. But did I actually have to do Pythagorean theorem, or is there another way that I could do it? And when I ask that, I mean, yes, I could have done trig. I could have forced trig on it. That would have definitely have not been the best way to do it, because I would have had to find the angle and then store and do all that stuff, but it wouldn't have given me the exact answer either. Any other ideas? It's a 30, 60, 90 triangle. From the beginning, we don't know any angle measures. Okay, we got to be careful not to assume, because we do fall into traps sometimes. But this triangle right here, if this is 10 and this is 20, this is S, this is 2S, so this has to be S times the square root of 3. That's the only thing mathematically that would work out, right? And so without doing any work, I know that if that's 10, that's 20, this has to be 10 square root of 3. And then I just double that to get this, and I don't have to do any work. All I really have is what's in pink, okay? So I want you to start learning how to visualize that stuff a little bit better. Now, I know that sometimes you think, ooh, I think maybe it is, but then you're a little unsure, so you'd rather just be safe. There's nothing wrong with doing this to be safe, because it'll definitely work. But see if you can start recognizing when you can do that. I definitely don't want you to go down the bad road of making everything special, because it's not, or assuming it incorrectly. Like even 3, 4, 5, sometimes we recognize incorrectly. For instance, if I did this, sometimes people want to go, oh, it's 5 because it's a 3, 4, 5 triangle. But that's not really what this is, right? Because 4 has to be the longest side. So things like that, you want to make sure you're not just jumping the gun, but start trying to at least make a prediction to see about what you would come up with.